Welcome to my talk. Today I'm very excited to talk about AdaEmbed, a system to efficiently prune large-scale recommendation models during model training. It offers large resource savings and better model accuracy. It's a joint work with Meta. Over the past decade, or even since the rise of the internet, our life has been greatly influenced by the recommendation model, like in social media and e-commerce. A recent study shows recommendation models take more than 50% of the training compute cycle and more than 80% of the inference cycle at Meta, meaning any resource savings can be a great deal. So, why does the state-of-the-art recommendation model take so many resources? Here, taking a social app as an example. To decide what posts to recommend to the user, the recommendation model relies on two types of features. The first one is the dense feature, consisting of continuous variables like time and age. They are typically input to traditional dense neural networks. But the second one is the categorical sparse feature, like post IDs. These IDs are sparse values. Say there's no ID like 1.5 or 1.1 between ID 1 and ID 2. Practical models often have hundreds of sparse features. To make these features trainable, we often use multi-dimensional embedding vector to represent each specific ID. So each feature associates with an embedding table with potentially billions of embedding rows. During model execution, we read the weights of those accessed embedding IDs and combine them with dense features to predict whether the user likes the post or not to make better recommendations. To limit the number of embeddings, we often hash each specific ID to the embedding row. But still, due to the large number of embedding IDs, the embedding weights can occupy more than 95% of the model size, requiring many terabytes of memory capacity across hundreds of machines for real-time execution. Moreover, as new embedding IDs can be generated over time, like new posts, we often need to continuously train the model to catch up the latest recommendation trend. Intuitively, to achieve better model accuracy, we want more embedding rows to represent more specific IDs. Here, this figure shows this accuracy improvement by using 2 times and 4 times more embedding rows over 20 days training. We want to know that any larger than 0.02 accuracy improvement means great benefit to production models. But this improvement comes with a great cost. The right figure shows this can slow down model execution by half if we do not add another dozens of GPUs. This is due to the increased memory, computation, and communication load in running more embeddings. So it would be great if we can achieve better model accuracy without allocating more embedding rows. But how to achieve this? Actually, for individual model inputs, only a subset of embeddings are accessed. And this figure shows rows have different access frequencies. Moreover, embeddings would have different embedding weights, meaning some rows may hold larger importance than others. On the other hand, the right figure shows these heterogeneous access patterns can lead to different access ratios of the embedding tables. We are seeing that some tables are overloaded and want more embedding memory to allocate more embedding rows to reduce hash collisions. Now, if we can have a scalable system to adaptively exchange the embedding memory to accommodate more important embedding rows, we may even achieve better model accuracy for that given resource. But it's quite difficult because as model training and the recommendation chain move on, all these heterogeneities fluctuate over time. So we introduced AdaEmbed to enable efficient embedding pruning on the fly. Thinking about model training across hundreds of machines, AdaEmbed interacts with the execution backend like PyTorch and manages the read and write of embedding weights. It uses the local agent to manage all embedding tables as a shared tool and wraps existing embeddings to minimize modifications. The embedding monitor captures the importance of each embedding role with the training feedback. Then, this local importance data is monitored by the coordinator, which orchestrates pruning across hundreds of machines. Later, this pruning decision is forwarded to individual workers, and the memory manager removes or allocates new embedding roles for different embedding IDs. But there are lots of practical challenges. Next, let's tackle the first one: how to identify the importance of each embedding role to current model accuracy. This accuracy is determined by the model output and ground truth. So we should think about which embeddings impact model output the most. During the aggregation of accessed embedding IDs, we are seeing that larger weights would have a larger impact. But now the problem is, once we remove an embedding role, we don't know its future embedding weights as the training moves on. Here, we introduce using the gradient to approximate weight values. Intuitively, a large gradient means we are adding a large update to embedding weights, which likely leads to larger weight values. Now, if we uniformly access each embedding, then larger weights mean a larger impact. But in reality, we access embeddings differently. To maximize the overall impact, we should also retain the weights of those frequently accessed embeddings. So eventually, we can formulate the importance of an embedding by taking the moving average of its aggregate gradient norm. Note that the importance of pruned embedding IDs are still updated over time. One beautiful thing of this embedding design is that we only need to update the importance of those accessed embedding IDs in that iteration, instead of billions, because others have zero access frequency. This can greatly reduce the system overhead. But here comes another challenge. There are billions of embedding roles scattered across hundreds of machines. How to prune introduces a very interesting trade-off. Intuitively, pruning in every iteration can catch up the latest embedding importance, meaning potentially better model accuracy. But this comes with a large system overhead. First, deciding which roles with larger importance requires orchestrating the decentralized importance values across many machines. In our deployment, when we need to allocate 5 billion embedding roles to 10 billion embedding IDs, collecting all the importance data to decide which 5 billion IDs with larger importance can take tens of seconds is hundreds of times slower than the training speed. To minimize this coordination overhead, we use a lightweight profiling design to figure out the distribution of importance values so that we can reallocate the embedding memory of those embedding IDs with smaller importance. Our profiling can decide the right portion of importance values to sample to ensure bounded error while reducing the system overhead. More details are available in our paper. Now, the coordinator periodically samples the importance distribution and initiates a new pruning round when it detects a big change in the importance distribution. This strikes a balance between pruning too frequently and too infrequently. However, as the total embedding size can be as large as tens of terabytes, we found each pruning round can reallocate hundreds of gigabytes embedding weights, leading to new system challenges. First, many of the existing embedding modules are built atop contiguous memory like tensors. So removing or inserting millions of embedding rows are pretty expensive. Also, we don't want to reinvent existing designs. To minimize this reallocation overhead, we introduce a shim layer to ramp existing embeddings, which is similar to the design of virtual memory. Here, we add a lookup table to store the metadata of embedding IDs, including the embedding importance and the address to their physical embedding weights. Now, the input IDs are first rotated to this lookup table to paraphrase the address to their physical embedding weights so that the read and write operations remain the same. This way, when we need to remove the rows of some embedding IDs, we do not deallocate the physical memory. Instead, we unlink this entry to its current address, and later we reallocate this address, say the embedded memory, to the newly reclaimed embedding IDs. All virtual memory can support the pruning of hundreds of gigabytes embedding weights at a sub-second speed. Now, it's time to assemble our system AdaEmbed for efficient embedding pruning during model training. It offers large resource savings by pruning large-scale recommendations on the fly. We evaluate AdaEmbed using a cluster of over 100 GPUs across 5 production models. We train each model over months of real-life data. In our evaluation, we care about the amount of resource savings and model accuracy. This table summarizes the results of those 5 production models, naming by their total embedding size from hundreds of gigabytes to terabytes. First, let's compare with the crafted model. The model is highly optimized by many experts. We are seeing that to retain the same model accuracy, AdaEmbed can reduce the total embedding size by up to 60%, meaning equivalent memory savings. This reduced model size can also accelerate the model execution by 1.3 times. Next, let's see what happens if we stick to the same total embedding size. Here, with AdaEmbed optimized embeddings, we can achieve better model accuracy. And here we want to highlight that any larger than 0.02 accuracy means a great benefit. Finally, AdaEmbed achieves all these benefits with less than 2% system overhead, which is negligible. Next, let's see what happens if we dig into the source of improvements. Here, this figure shows the real-time model accuracy over a 2-week training period. These 2 settings use the same total embedding size. Apparently, AdaEmbed achieves better model accuracy at all times. But here we also observe the diagonal variations in the model accuracy. This is due to the change in the daily user preference. On the other hand, this variation also highlights that we should adaptively accommodate more important embedding roles. And the lower figure shows this embedding allocation at a specific time across different features. Here, AdaEmbed can automatically search for better embedding configurations, and this configuration adapts in real time, contributing to the accuracy improvement. In our paper, we have more evaluations to compare against the different baselines, including the pre-training pruning and post-training pruning. To recap, AdaEmbed is a system to adaptively optimize the embedding for large-scale recommendation models. It offers better model accuracy while achieving large resource savings and less human effort. That's all from me today about AdaEmbed. Thank you very much.